Okay, good morning guys. So I'm here hoping to give you guys some help on acids and bases. So we're going to jump right in. Hopefully you've kept up with the reading and that you are today reading how to use formulas to identify acids and bases and how to predict products from a neutralization reaction. So here I've got two acids and I've color coded them, right? So that today we're going to talk about the difference between a monoprotic, a diprotic, and even a triprotic acid, right? So if we look here, you can see that both of these are acids because they've got some hydrogens in the front. Remember, our definition for an acid is something that donates a hydrogen ion, right? So when we put these acids in water, since they're ionic, they're not a covalent compound, they're going to break apart into their constituent ions. So for this one, each of these hydrogens is going to be an ion. So why do I have two of them here? Because there's a 2 in the subscript, so there are 2 hydrogen ions. And then whatever's left, my sulfate, is all by itself. So we've got one of these to 2 of my hydrogen ions. This is a nitric acid, HNO3. You'll notice that it's only got 1 hydrogen ion. So when we put this in water and it dissolves, it only has 1 H plus to donate. And then it's got its nitrate ion with its charge of -1 over here. So if we look at here, this one is a monoproton. So 1 proton, right? So it's got 1 hydrogen ion to donate. So it's a monoprotic acid. This one over here donates 2 hydrogen ions. So it is a diprotic acid. What do you think a triprotic acid would do? Hopefully you're thinking, hey, it would be something that donates 3 hydrogen ions. And a good example of that one is phosphoric acid. It's H3PO4. So when it breaks apart, it's got 3 hydrogen ions to donate. So it will break apart into H plus, H plus, H plus, and then since there's only 1 PO4, hopefully by now you've used these enough that you know our phosphate has a charge of -3. If there's 3 pluses, there's got to be 3 negatives. The only place the negatives can come from is this PO4. So its other constituent ion will be PO4, -3. Okay, so this is going to be important when we talk about balancing these reactions. So you're going to have some problems to work today in your assignment. And I'm going to work the first one for us. So we've got some reactions here that we are going to attempt to predict the products of in balance. Right, so if you do your reading, you know that when we react an acid and a base, we are going to get water and a salt. And a salt is just a fancy word for an ionic compound with whatever's left after our hydrogen and our hydroxide ions bond together and form water. So if we think about when we break these apart, when they are in water, they're going to break apart. They're going to disassociate. So we're going to be left with our ions. So if we look here, this is going to be an ion. This one's going to be an ion. And then if we look over here, this is obviously an acid. This one, we see this OH, so we should automatically be thinking base. So we've got acid and a base. So we see H is over here and OH is over here. H plus OH makes water, H2O. Or if you need to see it written another way, HOH. So you can see how those hydrogen ion and hydroxide ion come together to make the water, right? So then what happens to whatever's left, right? So if we look over here, I've got some Na ions and I've got some sulfate ions. So they are going to react and form our salt. So whatever's left after we make our water, our H from our acid and our OH from our base, whatever's left has to come together. But you have to remember your rules for how these ionic compounds combine, right? So Na has a charge of +1. I know that from the periodic table, right? I also know that from what it's stuck with. It's stuck with 1 OH. OH has a charge of -1. If it's stuck with 1 sodium, that means that sodium has to have an equal but opposite charge. It has to be +1. Hopefully by now, though, you remember how to use your periodic table to predict what our single atoms, what their ionic charge is going to be. So for our polyatomics, like the sulfate right here, the only way is to either look what it's stuck with or just memorize their charges. So I have SO4. If I look at what it's stuck with, they're stuck with 2 hydrogen ions. So each hydrogen ion has a charge of +1. So that means overall here, this charge is +2. If I have 1 sulfate ion, remember this is a whole thing, this thing has to apply the equal and opposite charge for my positive charge. So it's going to be negative, and since there's a +2 here and a negative has to come from this, this has to be a -2. So we've got SO4 with a charge of -2. So can these things come together and I be left with NaSO4? Let's talk about it. So 1 sodium atom has a +1 charge, 1 sulfate has a charge of -2. That's not going to work, right? So +1 and a -2, that gives me an overall negative charge, right? That would give me a -1 charge. We can't have that. So that tells us that there has to be some other mix where we're missing a positive charge, because remember, we want this to be equal. You can also do the loop and sweep, or the crisscross method that your book talks about when it talked about a couple modules ago when it talked about writing the formulas for this. Our charge over here is a 1. Right? So that means we're going to need 1 of the other thing. This charge is a -2, so that means we're going to need 2 of the other thing. Our formula for this guy is going to be Na2SO4. And if we look at our charges, Na has a charge of +1, but I have 2 of them, so that becomes +2. Sulfate has a charge of -2. +2 minus 2 yields 0, so we know that this is our formula. So our balanced equation, or our products for this reaction, because we haven't balanced yet, H2SO4 plus NaOH makes water and sodium sulfate with that charge. And then we'd have to, of course, go through and balance it. And that would be another step. Okay, so hopefully that helps you. This process works for all of our problems today. Let me know if you need any help.